Okay, hello everyone. My name is Ziyadzharif Alfarabi Kurniawan,
My name is Nicholas.
My name is
Hi,
Evandra Fadhillah.
and my name is Raihan Hermuhadzib.
and we are from Group One, and we're here to present our case study on the fourth case study for computational thinking O3. Next. All right. First of all, let's discuss the main problem. The president wants to build a secret communication network from the presidential office to the ministerial offices. This communication channel can be established directly between the presidential office, ministerial offices, or indirectly through other ministerial offices. The construction of this network requires sufficient and secure planning, considering factors that can affect the success of the communication channel. So first of all, we are splitting into the four parts. First of all, decomposition. Building on that order, to do this, first we need to find all the locations of the offices and the distance between them. Then we need to identify the terrain, as it's a big factor in deciding the shortest path. Some terrains require a large amount of time and money, so it will be more efficient to build around them. Rocket terrains, urban environments, and high water tabled areas are an example of terrain we should avoid. After all that, then we can start making the routes. These routes needs to be efficient and secure, meaning they should be built where people can't have the connection and secure enough for them to last a long time. As a bonus, building the most efficient network can keep the budget into a minimum. To ensure the connection stays up, the communication system does not go down. It means that it will be beneficial to have at least two connections to each office. This ensures the connection will stay up even if one of the channels is down as a backup.
Next
Next is
will
the
be pattern recognition. Finding a pattern to determine the shortest path to each office with respect to terrain. Do the same to find a path to the backup routes. Abstraction. Imagine the office as point in a graph and line connecting them is paths. Each area of the graph has weight to it, meaning the cost of the path are determined by the length and the location it's in. If it's located in a high weight area, the cost will increase. And finally, algorithm design. Use a shortest path algorithm, like the jig star, to find the most efficient route between the presidential office and the ministerial office. Factor in distance, terrain, and security. Plan redundant path using algorithm to find backup route, like k-disjoint shortest path, ensuring that the network stay function even if one path fails.
Now let me explain about the flowchart. So we start from the number of vertices and amount of edges, which is all of them are inputs, and then we continue. Then we split to parent rank list I, result mean cost and X. Then we continue to edges. Then so the edges is can be put at the input to list to U, V, and W. After that, we continue to the list append, parent append, and rank append. And then again, we continue to if amount of edges. We can go back to the start, or we can continue to list sort. After that, we continue to the local UVY, I plus Y and Z. Then we continue again to if parent Y. We can there are two there are two ways. You can continue again, or you can go back if uh you can go back to the start. But if we continue, you can denote to Z, and then you can continue or go back, and you can continue to if X uh, X and Y. Then you can continue and go back to the list sort. And if we continue again, uh, we can do E plus 1 and result append UVY, FUVW, and then continue to if rank Y equals rank Z. Then we can like split ways to parent Z and if rank Y and rank Z. If then in if rank Y and rank Z, you can split into two like split into two ways. To parent Y equals to Z and parent Z equals Y and rank Y equal plus equals 1. And then continue to if E and X minus 1. You can go back to the list sort or continue to I equals 0. And continuing to result I, main cost plus equals result I2. And then continue to I plus equals 1. Uh, and then continue to print result I0 plus main plus result I1 and result I2. Then continue to if I smaller than len result. Then if you can go back to the result I main cost, and then if you continue you to continue to print main cost, and that's the end of the flowchart.
Now, this is the pseudocode for the algorithm. Now, here, this is the initial to initialize the code. First, we have the graph, the class. This defines the amount of nodes that exist, and then we're going to put those nodes in a set of lists. Now, this is adding the paths. So we have the initial, which is U, final, which is V, and weight, which is W. And then we're going to add the paths to the list. And for the define main office, what we need is the parent, which the type is list, and office. Now, for the main office, we're basically finding the main parent. It's finding which of these nodes belong to. It's for union later, which yeah. So if the parent office is not the same as office, meaning that they're not in a union at all, then we're going to run the program again until we find the parent. And once we find the parent, then we'll return the parent office. Now this is combining the thing, which is we need a parent, rank, and a value. Now, if the rank of value 1 is higher than rank of value 2, meaning there's more nodes in the rank 1, then the value 2 would join with rank 1. And then this is if value 2 is higher, then this will value parent of value 1 becomes value 2. Otherwise, parent of value 2 is converted to value 1, and the rank is increased by 1. Now for the algorithm, we have the rank, which this is a list. So rank parent result is a list. Main cost is declaring that it's 0. We have I equals to 0 and j equals to 0. Now this is a for loop for office in range self.office. This is referring to the office, the nodes. It's keeping track how many nodes exist, and then based on that, it will create a rank, which will create 0 for each of the nodes. And for the parents, it will append its own number. So if it's like office 2, then it will become 2 for the parents. And then we have self dot list of lists dot sort key equals to lambda x what's it called, semicolon, no, it's colon x2. This is basically sorting based on the weight. And then while j is less than self dot office minus 1, this is basically keeping track of the paths. u v w equals to the self dot list of list I, and x equals to self dot main office parent of u. This is finding who the parent of the variable u, and y is finding the parent of the variable y. If they're not the same, if the parents are the same, then we would append the results and we will combine them so that the parents are the same. And then we add the min cost of the weight. And then we increase j plus 1 plus equals to 1, and then we increase the iteration. Now, after everything is done, it'll print the edges. It'll print out the result of u, v, w, and it'll print this out in the next slide. In the next slide, this is the driver code. If we add these paths, this is what will be outputted. So 2 can be connected to 3, and 0 can be connected to 3. 0 can be connected to 1, 4, 1, and the weight is here, and then we total the weight. The big O notation, oh yeah, this is considered a greedy algorithm because it finds the highest value locally, most efficient. The big O notation the big O notation is loop, which is it's n squared, and yeah, summary.
All right, so lastly is the summary. Building a secret communication network from the presidential office to various ministerial offices requires us a lot of preparation, avoiding expensive terrains in route planning, designing short and secure paths to minimize costs, and ensuring each office has 2 connections for reliability. We use graph algorithms similar to crisscross algorithm to find optimal and redundant path for the communication network. Unfortunately, this is an online presentation, so we cannot give you an answer any questions you may ask. But that's it all from us. Thank you so much for listening. We're out.